moving on from chi-square testing, it's going to seem like we're backtracking a little bit because we're once again going to be talking about confidence and significance testing. So, last time we talked about confidence intervals and significance testing, we were doing that in the context of p-hat, okay? P-hat, if you don't remember, is the sample proportion, all right? In those problems, we were given a sample. We worked with that sample exclusively. We had to find a couple different things about it. We could find p-hat and then do confidence intervals or a significance test. But that was only based on a small little sample. What we're going to be doing now is we're working with entire populations, so a much bigger number of people. So essentially, we're going from small groups to big populations, and that's why confidence intervals, what we know about them right now, doesn't apply to what we'll be learning today. So we have a new formula because we can't use the old formula because we're not working with p-hat anymore. We need some new things. So p-hat is being replaced by this x bar right here, all right? And I'll tell you what all the different variables mean here in a second. So we have x bar plus or minus z times s over the square root of n, all right? And this all equals mu. This little u symbol right here, that is the Greek symbol mu, and it just stands for the population mean. So what we're doing is we're doing this confidence interval, and that gives us an idea of what the population mean is, okay? So what do all these different variables mean? X bar is the same mean. All right, we're still going to be given a sample and numbers on the sample, and then we have to take the average of that, and that is X bar, the sample mean. It's just the average of the sample. Z is the critical value. This actually does not change from the last confidence interval formula we have. Remember, depending on our level of confidence, Z will change. So if we have a 95% confidence interval, Z is 1.96. If we have a 90% confidence interval, Z is 1.645. 99% is 2.58. Remember that table I gave you guys in your old notes? That Z is still does the same thing here. S is the standard deviation of your sample, okay? So you're given a sample, and then S is its standard deviation. And then N, as always, is your sample size. So anytime you're confused when working through this formula, you don't know what one of the variables means, you can always come back to this list and it'll tell you. One of the reasons why we need this new formula is because these variables might not always be strictly given to us. Like instead of saying, oh, I have a sample of 1,000 people and 200 are doing this specific thing, it might say we have a sample of 200 people, but they're doing a bunch of different things. So that's why we need a new formula, because it's not just one specific thing we're looking at anymore. So using this new confidence interval formula, we can calculate confidence intervals for an entire population. That's kind of the whole point. Also, we can use this formula even if we're not given all of our information up front. We're not going to do that today. I'm going to ease us into that, but that's why this formula is better than our old one. So first example of working through this formula. So the National Assessment of Educational Knowledge, or NAEP, gives a short test on math skills. Scores on that test can be anywhere from 0 to 500. Let's say that recently in SRS just stands for Simple Random Sample. So recently an SRS of 840 men was taken. Their mean score, so the sample mean, the mean of the sample, X bar, is 272. And the standard deviation of their scores was 59. Using this data, what can we say about the entire population of 9.5 million men? I want to find a 95% confidence interval on this.